Hi, I'm Hao. I'm super excited to present our work, Information Bottlenecked Variational Autoencoder for Disentangled 3D Facial Expression Modeling. Our main contributions are threefold. The first is that we use the point cloud transformer to take the advantage of the attention-based mechanism and remove the need of mesh topology by processing point cloud data directly. Secondly, we use a mutual information regularizer to improve disentanglement performance. Thirdly, we apply a conditional VAE plugin to our original VAE to further extract semantically meaningful latent variables. To form the problem, we show a typical 3D face reconstruction autoencoder, where the method is trying to reconstruct exactly the input. It usually uses a latent code as a compressed representation of the input faces. And our method does the similar thing, but with identity and expression disentangled. That means we extract two sets of latent code at the same time, with each individual latent code representing identity or expression separately. And we have two decoders to reconstruct the corresponding 3D neutral faces and the input at the same time. This is the architecture we propose. The left part represents our encoder, which is the point cloud transformer. Enabled by the variational autoencoder architecture, we can then separately sample identity latent code ZID and expression latent code ZEXP from the output of the encoder. For the loss function part, we apply the mutual information regularizer to the ZID and use two reconstruction losses on identity faces and full faces respectively. This is to achieve the reconstruction goal. The part in red color is the additional conditional VAE plugin that uses additional label information for semantically meaningful disentanglement. On this page, we show the core theoretical idea of this paper. The information bottleneck objective function, firstly proposed by Tishby, has two sub-objectives. The left-hand side one maximizes the mutual information between the identity latent code and the reconstructed identity face. We strengthen this part by multiplying identity reconstruction loss by a scalar that is larger than 1, resulting in higher reconstruction accuracy. The right-hand side one minimizes the mutual information between the identity latent code and the input face. We directly estimate this term via batch-based sampling method, thus form a mutual information regularizer LMI, resulting in a more compressed identity latent code. Then I'd like to show some demonstrations of our work with the conditional VAE plugin. In this video, the identity latent code is keep changing without involving any expression changes, and we can see the reconstructed full and identity faces are identical because no expression is included. Then we change the semantically meaningful expression latent variables. You can see that we can make the reconstructed faces to do different expressions. We demonstrate 4 expressions here: the bare teeth, the cheeks in, the eyebrow, and the high smile. In the end, we can also make a combination of 2 expressions. Finally, we show the disentanglement results compared to previous state-of-the-art. We outperform them by a large margin, especially on the CoMA dataset, because it contains a large amount of 3D scans of the same subject, where our mutual information regularizer performs expressionally well. To conclude, we make a semantically meaningful disentangled facial expression modeling. Our mutual information regularizer works very well for learning a many-to-one VAE, and future work can include finding the Pareto optimal solution for the 2 sub-objectives in the information bottleneck structure. Thanks very much for listening.